Thank you, David. So, see if the pointer works. Do you have a pointer? David, do we have a pointer? With clicker. Is it this? Can't be that. How do I control the slides?
I think this, yeah.
Okay, that's there we go. Thank you.
So it'd be that way.
All right. All right, sorry about that. It's a little bit different from what I've seen before. So my name is Ananth Natarajan, and I'm going to be talking about how machine learning and AI can make oil and gas projects better in terms of performance. And why is this important? This is important because of that. Now, what you see on the chart there is the upstream investment per year over the last 10 years. In 2014, we spent almost $1 trillion on upstream spending, and we've been spending about $500 billion each year for the last few years. And by way of introduction, the two blue corners of the histogram, the dark blue and the light blue, is where I spent my career for the last 20 years. I started off in offshore deepwater R&D, and I ended up managing offshore projects for about 10 years or so. And this is why, this is the other reason why what we're talking about is important. This chart was from a McKinsey report that was published, I think, 2 weeks ago or so. You can see the track record of projects in different sectors. Now, if you added up the projects in the previous slide and did some kind of an NPV analysis or something, you would probably come up with a few $1 trillion of investment in the last 10 years. And this chart essentially shows on the x-axis the schedule delay versus the planned schedule, and the y-axis shows the cost versus planned cost. Now, what you see here is oil and gas. So oil and gas is approximately about 70% or so over budget. That's the average track record for an oil and gas project, about 40% over time. The overtime also translates to cost as well, and I'm sure that the 40% overtime probably translates into more of an absolute cost than the 80% over budget. David was mentioning how analysts don't believe that we can execute our projects on time in the oil and gas sector. But this is not just us. You can see the other sectors as well. Some of them are quite a bit worse. So if you just compare the investments into projects, into mega projects, especially in our industry, versus their performance, you can see how even a marginal improvement in this track record can lead to a great amount of returns. And this is also more critical because of the declining investment in upstream projects. One thing that is not declining significantly even in the next few years or next few decades is the demand for oil and gas. So we essentially have to find and produce these assets with a lot more efficiency than we ever did. And this is also why I'm doing what I'm doing now. I have a startup called Siberium, as David said, and we are focused on improving mega project performance using AI and blockchain technology. This is the map for my talk, so I'll get into what projects are, what their nature is, what their track record is, why do they show that track record, and how can we improve that track record using AI and machine learning. Projects are not just confined to oil and gas, of course, as we saw before. Projects abound in every sector. Projects are fundamental to the human way of life. Projects are responsible, mega projects especially, are responsible for creating energy, transportation, infrastructure, etc. that underlies the human way of life. And in a sense, you can say that mega projects underlie human civilization. We see trillions of dollars of spending each year on mega projects, and we also see trillions of dollars lost due to project inefficiencies. Now, let's see what projects are. According to the PMI, this is the PMI definition, the Project Management Institute. They are temporary in the sense that there is a beginning and an end. You have a project beginning at which time you have a certain cost, a certain budget that's allocated to produce certain benefits in a fixed amount of time. The track record, of course, shows that we exceed that amount of time, we exceed the amount of cost, and often we also have issues with what is finally delivered versus what was planned to be delivered. So we have problems with all the three buckets of performance, project performance. When we look at capital projects, we are talking about networks. We are talking about networks of independent entities, contractors, subcontractors, vendors, clients, regulatory authorities, and so on. Each one of these entities has their own self-interest. Each one of them is an independent legal entity. And this is the reason behind the economic value that's created by projects, by capital projects, as well as the cost for the issues that we see with them. And this is, of course, the final part of the PMI definition. Every project creates a unique asset in some manner. All right, so this is just to show the kind of headlines we're used to. This is just a typical kind of news headlines we see. So it's not just our sector. Projects show this terrible track record across every sector that you see on the news. Again, that's some more statistics. One interesting thing that to highlight here is IT projects. IT projects, we don't often think of big IT projects when we think about capital projects, but IT projects probably have the worst track record in terms of cost overruns. I mean, there was a study that showed that they have almost 100% cost overrun. So essentially, that is not just oil and gas projects; it's projects as a whole. Getting into oil and gas projects, this is the typical. Approach to planning and executing them. Projects follow a stage gate approach, so you have an identification phase, followed by a few phases through which projects are progressively elaborated. You have better defined schedules, better defined costs, and so on, until finally at a final investment decision stage. This is the terminology in our industry. Funds are actually committed by a promoter or a consortium of promoters to realize something like an offshore platform in a certain amount of time. This is the track record of offshore oil and gas floating projects. This is from a paper that we had published in January in the Project Management Journal. There's a few interesting things to note here. You do see the high overruns because the overruns, the average overruns of the cost overrun of 30% that you see in the sample of approximately 25% of all the offshore oil and gas projects that have been installed so far amount to almost $100 billion of cost overrun. And that's not even speaking about the schedule overrun. Now, the other things to note about this chart is that this is not a normal distribution. This is a fat tail distribution. A fat tail distribution essentially has a fat tail. So in a normal distribution, the tail tapers off quickly, whereas in a fat tail distribution, which is typically modeled using power laws, there's a significant number of outliers which show extremely high overruns. So on the x-axis, the 1 stands for 100% overrun, 2 for 200%, 3 for 300, and so on. And there is even more extreme outliers. The fat tail essentially contains what is called black swans in the common terminology. We have even more extreme overruns, which in some statistical papers are called dragon kings, and these are the bumps in the tail. These are the projects that show overruns of 200 or 300%, and these are the projects that, when they show this behavior, would put the future of a company at stake. Many companies in our sector have faced this situation quite often. All right, so this is again the same data that we saw earlier. Each one of those dots that you see is a project. You have the schedule overrun on the x-axis and cost overrun on the y-axis. We use a clustering algorithm to classify projects, and we can see that as the projects veer towards extreme cost or schedule overruns, they separate out into distinct populations. There is limited collinearity between cost and schedule overruns. So this was actually quite an interesting finding that we did when we did that analysis, which was published, like I said, in the Project Management Journal. And you can also see like Dragon Kings and Black Swan projects, distinctly taking shape. Once again, the 2 on the x-axis is 200% overrun, 3 on the y-axis is 300% overrun. All right, so why is this the case? I mean, why do we see this track record, not only in our sector, but in every other capital project segment? Complexity. Complexity essentially means emergent outcomes. Emergent outcomes cannot be forecast, so this is a fundamental limitation to project planning. Biases, human cognition has limitations when it comes to complex systems in terms of processing ability, but also in terms of biases such as how we estimate schedules. We are very prone to things like optimism bias, and this again builds up across these contractual networks. Principal agent issues refers to the conflicting incentives. So a contractor across every contract is incentivized to quote the lowest cost and time to obtain the project, but they are also incentivized to maximize the gains from the project and the time they spend on it as well. And again, this is present across all the hundreds of contracts in a complex capital project. And these three issues essentially affect each other and lead to project underperformance. And now let's get into complexity. Like I said, complexity essentially means that there is a fundamental unpredictability to complex systems because of emergence. Projects are complex systems. Just going to quickly breeze through this slide. We've known about unpredictability in complex systems such as societies, economies, and so on for some time. I mean, there's been a lot of work that's been done by mathematicians, economists, and so on. But when it comes to project planning, we still somehow forget the fundamental unpredictability of projects. We assume that when we have a budget, that's more or less how we expect a project to go. When you speak of black swans, we need to mention Nassim Nicholas Taleb, who coined the term. So he had this interesting table in his book. I mean, when he was talking about systems in which forecasting can be, forecasting is not very reliable. You can see that most of the systems where forecasting is difficult is complex systems, complex economic and social systems, and so on. All right, so the next bucket, biases. There was some talk earlier about behavioral psychology, and these two gentlemen there are Kahneman and Tversky, whose work in the 1970s led to our current understanding of how heuristics and biases and errors from heuristics and biases that humans use proliferate in economic systems. They also had a few recommendations with regards to project management. I mean, they essentially pointed out that in order to correct the biases that we are prone to, it is important to look at the past track record of similar projects. Some of the important biases for project management, like I mentioned before, are optimism bias, availability bias, where we tend to concentrate on things we know and not what we don't know, and so on. This is just a list of cognitive biases. We know a lot more about these things now since we started the work. So let's see how we can remediate this situation. So this chart essentially shows the history of analytic methods in project management. Almost 100 years ago, Henry Gantt came up with the Gantt chart, which we still use today. In the 1950s and 60s, we saw a lot of growth in project management as a discipline and in the growth of analytic methods in project management. And this was because of a lot of the defense and aerospace programs around that time, like the Apollo project, for instance, and a lot of other defense-related programs. The American Association of Cost Engineers was founded in 1956. The IPMA and the PMI, the two largest project management societies in the world, were founded in the 1960s as well. Analytic methods such as the critical path method, the PERT diagram, and so on date from that time period as well. In the 1980s, we start seeing more and more application of computers for project management. We see the launch of what became Oracle Primavera and MS Project in the 1980s. These are still used today to manage capital projects in our industry, the oil and gas industry. And in more recent years, we've kind of seen like how this is moving to the cloud. So essentially, these computer-aided methods are still implementing these earlier methods. So we still visualize schedules in the form of Gantt charts and PERT diagrams. We use the critical path method and so on. But as we mentioned earlier, there is a lot of limitations to this approach. One is that these are all estimates and activities that are planned within a project. And within project planning has limitations in terms of forecasting, forecastability because of complexity. There is also limitations because of cognitive biases, because we do underestimate time and cost. And again, this proliferates across these networks. The other thing, of course, is principal agent issues, where there is a deliberate element to understating costs and time as well across contractual networks. So AI and machine learning will help because it helps you to look at the track record of previous projects in order to correct the errors that are made in project estimates. And it also allows you to look at the project networks, and these are complex networks, and try to understand the nature of risk, how risk is built up, how it flows, and predictive analysis of how risk can build up in a project and how it can affect your cost and schedule outcomes. In the future, I'll just briefly introduce blockchain because I think, because as I will say, I mean, as I'll point out, blockchain is going to be a transformational force in project management when it matures in the coming years. So I will be focusing on a machine learning method for project forecasting, and I will talk briefly about some of the methods. So this is what is called reference class forecasting. So the recommendation by Kahneman and Tversky to look at the track record of past projects in order to correct in-project estimates was developed into a methodology called reference class forecasting by Professor Ben Flubier, who is one of the world's predominant experts on mega projects. So how does it work? So this is a cumulative probability distribution that was generated from the track record of offshore projects that we saw earlier. So essentially what you have on the y-axis is uplifts, project uplift to schedule and cost. And on the x-axis, you have the probability of cost or schedule overrun. So if you have a 0% uplift to your schedule on an offshore project and during FID, according to this chart, a 0% uplift would result in approximately a 75% probability that you're going to have a schedule overrun, and similarly for the cost, you would a 0% uplift is correlated with approximately 85% chance that you'll see an overrun. So the way that you would use this to manage your risk is to uplift your schedule and cost estimates. If you were to do a if you were to work with a 50% or less probability of your project exceeding its schedule, okay, I guess I pressed the wrong button there. Let's see. All right. So if you wanted a 50% or less probability of your project exceeding your schedule, you would do a schedule uplift of approximately 20% because that is the track record of offshore projects. And this is essentially, this distribution points to the deviation of actual cost and schedule from planned cost and schedule. So any offshore project would be subject to this curve. Now, one observation that we have is that projects are, the probability of overrun in a project is related to several project features. For instance, in offshore projects, it has been shown that the location of a project, the complexity of a project, and so on is correlated to the possibility of overrun. Whereas using RCF, RCF has been quite successful, by the way. It's increasingly being used in Europe, and it has been shown to be superior to other methods such as Monte Carlo. But still, RCF, the same curve is applicable to every project in its class. So this project would be used to generate uplifts for any offshore project that is being sanctioned. Now, how can we make that specific to a project by relating project features to the probability of overruns? We use machine learning to do that. So while RCF looks at the actual, this is the planned cost and schedule as the track record that it learns from, we use a machine learning model that not only looks at that track record, but it also looks at project features that affect the project overrun And along with the track record and these features, it is able to generate probability curves specifically for each project. And we'll see how this works. This, by the way, is the features that we use in our machine learning model for offshore floating projects. We use approximately 18 features, and these features all, they are not only related to the probability of overrun, but they also interact with each other in complex ways. And this is why we are using a machine learning model to do this and not a deterministic model, right? So here is how, here's an example of how this would work. So we have 5 projects here. Basically, each column is for an individual project. Column number 4 is a project that is weighted towards underruns because it's in shallow water, there's low novelty, high lessons learned, and so on. And when we apply our machine learning model, this is what happens. Now this is for schedule uplift. So this was generated by the machine learning model. The thick black line that you see is the RCF curve that applies to every project in its class. So the machine learning model took that and redrew it for every one of those 5 projects. Project number 4, which was weighted towards underrun, is below the RCF curve. So if you had a 0% uplift to the schedule there, you would have a 50% or less chance of overrun. Whereas project number 5, if you wanted a 50% or less chance, then you would have to uplift the schedule by about 30% or so. And similarly, we see the same thing being applied to cost as well. So essentially, we have project-specific risk curves. So this not only allows you to quantify the risk per project, but you also can go back and look at the relationship between project features and the risk curve. So as you're developing a project through those stage gates, you can see how changing each of these features will affect the risk curve for the project, and ideally you want to have the risk curve below the RCF curve. I'll talk briefly about other applications of AI to project management and project efficiency, some of which we are working on. So like I said, projects are networks. Projects are, now that's a level 2 schedule for an offshore project. See about 200 milestones there. So projects are interconnected networks. So this is a network of milestones. We can model how milestones are connected to each other. The connectivity between milestones affects the risk of the milestones and how this risk propagates across these networks. So we are taking a few steps from the critical path method that has been used for the last 50 years or so. And we are operationalizing several new means of understanding risk in these projects. So for instance, the risk profile at an individual milestone, the shape of the risk curve is related to the connectivity of that milestone and other factors such as the length of the milestone and so on. And we can understand these curves better using machine learning methods. We can understand how to manage these milestones better. We can understand how risk can happen we can do predictive analysis of risk issues essentially. So even during the execution phase, if something changes with regards to what was planned, you can see what kind of outcomes that could generate. And since we're doing a lot of this work for the first time, we are finding quite a few interesting things. So if you model anything on the project network, so for instance, if you model the duration of each milestone, if you model the connectivity of each milestone, quite interestingly, we observe that same fat tail distribution with Dragon Kings that we saw in the project track record. So this is almost like a fractal pattern that keeps recurring through a project network. And this was quite an interesting result, and this probably relates to the nature of risk in projects as a whole. All right, so I'll quickly introduce blockchain the next couple of slides. Like I said, blockchain technology will really address some of the key issues with why projects have that terrible track record. They can create a distributed system, a trusted source of truth across this entire complex project network. So you can synchronize all the schedules, the contracts, and payment systems of the project into one system across all the stakeholders. Smart contracts are another technology that will change the way that projects are executed. Smart contracts can logically represent project contracts, which in our industry, are huge documents that take months to negotiate into more simplified and logical programs that are executed when certain conditions are met, and the relation between this and legal contracts is something that will change the way that projects are executed, make them a lot more efficient. Tokenization, project assets, project created assets will be tokenized in the future, and other aspects of projects such as ESG credits and carbon credits and so on will also be tokenized on the blockchain. And all of this information on the blockchain will improve the ability to use AI. A big issue with projects is the availability of data, but the quantity and the quality of data from projects is quite challenging. Blockchain will make a huge difference to that as well. And all of this together will definitely make a big difference to that track record that we saw earlier. So we will make a significant difference to those 80 and 90% overruns that we saw across project classes by using this combination of technologies. Adapting a blockchain architecture to project management is a non-trivial task, because there are several aspects of blockchain that are at fundamental variance with projects. You cannot have permanent records, because projects are subject to change. So any block that represents a contract and so on a project should be easily changeable, and public blockchains are not very good at doing that. And also the projects are basically DAGs, directed acyclic graphs, so each block has more than one predecessor and so on. So the adaptation of blockchain technology to project management has to go back to the fundamental aspects of cryptography that underlies blockchain. And we did describe that in another paper as well, so that's also publicly available, and I can definitely share that if anyone is interested. All right, so that's all I had, and if anyone is interested in any of these things, AI, blockchain, or even if anyone wants to talk about complexity theory or about behavioral psychology and so on, please do get in touch. So my contact is on there. You can also scan the QR code, to get your contacts on your phone. And thank you. Yeah, thanks, Steve.